Hello everyone, and this will be the first part for the graph series. This will cover the things you need to know for graphs. In the next video, we'll cover graph algorithms. So first off, what is a graph? A graph is a series of vertices and edges. This is what we call a vertex. Vertices is the plural of vertex. So this vertex, this vertex, this vertex, this vertex, together they're vertices. This we call an edge. The connecting line between two vertices is called an edge. So this is a vertex, the plural of vertex is vertices, and this is an edge. Okay, plural of edges, edges, but you all know that. So, okay, what is this out degree, in degree I've written here? Well, first off, you see this graph, we call this a directed graph because the arrows point somewhere. The out degree is the amount of arrows pointing out from a vertex. So for instance, the out degree of 2 would be 2, and the in degree is the amount of arrows pointing into a vertex. So the in degree of 3 would be 2. This structure here is with two arrows, one arrow this way, one arrow that way. We call this parallel edges because they're like parallel lines, you know what I mean? Just pointing in different directions. So we call that parallel edges. So I'll probably like leave that there. Parallel edges. And then I'll call this one, circle it. This is the inner loop. Or sorry, not inner loop. This is the self. I don't know if there's much on that, but I think I'm here to teach you graphs, so it's important to know that. Okay, so this graph, these arrows, we call, I think I mentioned this already, but we call this a directed graph. Right, so these graphs, arrows, they point somewhere. These graphs edges kind of look like arrows, right? They point to a direction. So what does that even mean? Well, if I was at A, I can either go into this loop, so there's probably like an error here or something. Either I can go into this loop and come back here, or I can go here to, I'll say this is B, and this is C, and this is D. So from this point A, I can either go here, I can go here, I can go here. So you're just following the arrows, right? Could I go to D from A? No, because this arrow doesn't point out of D, doesn't point out like this. No, it points into A. It doesn't point out of A, it points into A. So if I was on D, then I could go to A, but not the other way around, right? So these arrows actually mean something. You have to follow the arrows accordingly. The next type of graph is the undirected graph. So I have A, B, this C, D, and then this will be E. Well, now they don't really mean anything. There's no arrows, right? There's no forced direction I have to take. I can go this way, so I can go A to B, or I can go this way. I can go from B to A. I can go from A to E, following this line, or I could go from E to A, following the exact same line, I'm just starting at E this time. Okay, and last thing to mention is you cannot combine two different types of graphs. I cannot make this an arrow and have the rest be undirected. You are either fully directed or fully undirected. So let's move over to this next type of graph. So you saw in this graph up here, right? It was a directed graph, but I had parallel edges and a self loop. A simple graph is a directed graph without parallel edges, so I'll just write P edges. And it's without any self loop. But it's still directed. So you kind of view it as a simpler version of a directed graph, right? Without all the confusing stuff that you could have with direct graphs like parallel edges or self loops. It's just arrows pointing in direction. Call this A, maybe B, maybe C, maybe D. So this is what we call an unconnected graph. There's two sections here, right? There's section 1 of the graph, and then there's this other section of the graph. They're two separate sections. Right? But let's say I want to connect them. Let's say this is B, and then this is C, and everything else doesn't really matter right now. Let's just say that's B and that's C. Well, if I were to draw a connecting line like this, we call B and C as articulation points. So this is simply, they're just called articulation points. So essentially, what they essentially mean is like, hey, B and C are crucial points to connect this graph with this graph. If this edge didn't exist, or if we deleted B and then deleted C from our graph or something, right? I don't know, and of course deleted the corresponding edges, right? As you'd have to do. There'd be no way to go from this graph to this graph. But look over here, and these strongly connect. And we also call this a weak. I don't know if that's the physics terminology. When you have an articulation points, when you have like just one line connecting them to. Oh, disclaimer: B and C are the articulation points, not the edge BC. B and C are the articulation points. Okay, not the edge BC. I'm messing up my wording, so it might be confusing. But yeah, when we have a graph that has like this, when we have multiple connections to this section 2, I'll say maybe to section 1 and section 2, when you have multiple ties to it, right? This is AD and this is C and it's like BC or something, I don't know. Well, then you don't have any articulation points, because if you were to get rid of this and get rid of this, we still have a connection through A and D. If you were to get rid of this, get rid of this, we still have a connection from B to C. So you can't have any articulation points. Articulation points only exist when like the connecting points B and C are the, without them, like there's no, it becomes unconnected fully. Okay, so it's like a with these articulation points, we have them being weakly connected. Without them, it's fully unconnected. Here, if I move B to C, it's still connected through A and D. So you don't say you have any articulation points here. What made that clear? And this is strongly connected because you have more than one connection. That's why this one was weakly connected with the articulation points, because we only have one connection, or one edge connecting the two graphs. Whereas this one, we have two edges. So that's pretty cool. Now, before we before we dive into the next set of graphs, I would like to discuss the cyclic and acyclic graph. The cyclic graph is like this. So it has some requirements. You have to have three distinct nodes. Three distinct vertices. I say vertexes, but that's not proper. Three distinct edges. I guess you could say just three edges in general connecting them. I'm gonna say distinct though. I must have the start node equal to the end node. This is the definition of a cyclic graph. So for instance, ABCD is a cyclic graph. So I can go from A, and these are at minimum tree, okay? So we're at A, and then we go to B, and then we go to C, and we go to D, then we're back at A. Does this meet all the requirements? Are there at least 3 distinct vertices? Yeah, we have A, B, C, and D. That's 4. We're good. Do we have at least 3 distinct edges? So we're going from A to B, which is one edge, B to C, which is another edge, C to D, which is another edge, and then D to A, which is another edge. So we have 4 distinct edges. We're good. And the start is equal to the end. Like, this is mainly the important thing. Okay, start is equal to end. This is a bunch of yap, to be honest. Just know, hey, I'm starting here. Hey, look at that. I have a direct connection to the end just by this node. It's almost as if we're going in we can go in a cycle, right? Because we can, right? We can go A, B, C, D, A, and then we can go back to B, C, D. It's a cycle. Acyclic, there is no cycle. I could go A, B, C, D, but there's no way for me to go from D to A. Just basically look at the direction of the arrows, right? This is pointing downwards, so maybe I could go A, D, and then be stuck, right? But there's no cycle here. There's no way for start to equal end. Now, I didn't really mention cyclic or acyclic graphs for an unconnected or for undirected graphs, but they exist as well. This is an example of a cyclic unconnected graph, right? It meets all the requirements. It's A, B, C, D. You would go like A, B, C, D, A. Life is good. Look, we're starting ending the same thing. We're going through like 3 distinct nodes or vertices. I tried to do like maybe A, because the thing with direct undirect graphs is you can go both directions, right? If I said, okay, boom, A, B, A, and now I have a cycle. No, you don't. The definition of a cycle needs to have 3 distinct nodes. So for an unconnected graph or undirected graph, it is important to pay attention to that. Right, we only have 2 distinct nodes. You have A, B. If I said perhaps A, B, C, B, A, would this work? We have 3 distinct nodes, yes. But do we have 3 distinct edges? No, we have A to B, which is the same as B to A. Then we have B to C, which is the same as C to B. So we only have 2 distinct edges, so we don't meet all the criteria that we set. Okay, so now we understand the concepts of a cyclic and acyclic graph. I'd like to go over the directed acyclic graph that looks something like this, right? So it's in the name, it's a directed graph that's acyclic. The important thing about this graph is that for a directed acyclic graph, or a DAG, right? You can take any DAG and turn it into and make it look like a linear line. You can kind of linearize it. We call this linearization topological ordering, not sorting, ordering. Make sure you know this because it's literally on the 2025-2026 topics list, topological ordering, right? That I know it's pretty easy to just direct to a cyclic graph, so you can locally just grab this graph is cyclic or not. And then look here, right? Topological ordering, what is that? I'm able to arrange this tag ABCD into a line like this, right? A connected to B, or A leads to B, B leads to C, C leads to D, in a linear fashion. Like this is linear. Now, what's important about this? You might be wondering, Sid, can I even do stuff like this? Where I have A all the way to D and B all the way to C, like in this red? Yes, that's allowed, as long as it's going in this direction. Your arrows must be going in this direction. If I had D to C, this is illegal in topological sorting or ordering. They'll have to go one direction. This maintains that linearity, right? Everything's going in this way. Cool. That is topological ordering. It's really easy, to be honest. Maybe the name might throw you off, but it's just like A connected to B, B connected to C, C connected to D, and oh, we need to draw an arrow from A to D. Oh, we need to draw an arrow from B to D. And if you get any back arrows, you know you're dealing with a cyclic graph. Okay, so that's literally all we need to cover in terms of types of graphs, but there's a little bit more you need to know about graphs. Let's talk about adjacency graphs. We really care about adjacency, like Did I even spell that right? There's no way I spelled adjacency right. That seems spelled so wrong, bro. There's no way that's real. Yeah, adjacency like this. Okay, so adjacency in a undirected graph will look like this. Why is this here? Right, you can say A and B are adjacent to each other because they're connected by this line. So A is adjacent to B, and then B is adjacent to A. And it is just from the idea that you can go from A to B and B to A. That's what adjacency is. Going from one node to another is adjacency. Just from one edge. Looking at this graph, right? You can say A is adjacent to B because we can go from A to B. But can you say B is adjacent to A? No, you can't because you can't go from B to A. You could say A is adjacent to D because you can go from A to D. But could you say that D is adjacent to A? No. In this case, D is adjacent to nothing because it can't go anywhere. It's essentially just like from your node, where can you go? Any nodes you can go are adjacent nodes. Okay, so adjacency is a really big, important topic. A lot of algorithms that we're going to discuss later, or they don't, I won't say they really look at that, but at least breadth first search and depth first search focus on adjacency. So let's talk about the two ways that you can track adjacency, right? The first is what we call an adjacency matrix. So you're going to take your vertices. So let's just use this simple graph right now. You know what? Let's make a new graph. I'm going to make a new graph. I'm going to make it directed. Let's add some of this. Let's add one of these. Let's go like this. Let's have a node here. Let's connect to this. Let's connect to this. Let's connect to this. Let's connect to this. We're just connected to this. And we have a value here. It's only connected to this. Okay, so this is going to be the graph I make my adjacency matrix on. A, B, C, D, E, and F. So the matrix, what are its rows and columns? They're going to be your vertices. So we're going to have A, we're going to have a B column, a C column, a D column, an E column, and an F column. And conversely, you're going to have an A row, a B row, a C row, a D row, a E row, and then lastly an F row. Okay, is a node adjacent to itself? No. So A is 0, B is 0, C is 0, this is a C. D is 0, E is 0, and F is 0. Is A adjacent to B? Yes, because there is a way to go from A straight to B in one edge. So we can say this is 1. When you're adjacent, you fill a 1 in. When you're not adjacent, you fill a 0 in. That's why you filled zeros in here, because you're not adjacent to yourself. A is not adjacent to A, B is not adjacent to B. Okay, is A adjacent to C? No. There's a way to go from A to C by following this, but adjacency, you have to just be able to go from one node to the other in just one edge, right? Can you get from A to C in one edge? No, you can't, so this would be a 0. D, again, no. So I could go from two edges here to here, but that's not one edge, and the requirement is to go from, for A to be adjacent, you have to some node. A has to be able to reach that node in one edge. So then E, well, E would be adjacent because we have this edge connecting A to E, and then F would also be adjacent because we have this node connecting A to F. And I'll write my A's in the simplistic way. I like that way a little bit better. It's quicker to write. Okay, B. Is B connected to A? Yes, there's an arrow going from B straight to A. Is B connected to B? No, you cannot be connected to yourself. Is B connected to C? Okay, it's an arrow, but is it going from B to C? No, it's going from C to B, so that doesn't work for B. B is not connected to C. Right, B can't use this arrow to get over to C, you just can't, because the arrow direction matters, but we already discussed that. Is B adjacent to D? No, it takes 2. hops to get over there, I guess. Is B adjacent to E? Yes, it is, because it's only one arrow away. And an F? No. I believe the only way to get to F is from going to A. So it could go like in 2 hops, but again, remember adjacency, you have to be one edge away. Okay, A to C. Or C, is C adjacent to A? No. There's no way for you to get from C to A in 1 hop. You have to go here and then follow this line here. Is C adjacent to B? Yes. So no, even though B wasn't adjacent to C, because there was no error here, that doesn't mean C is not adjacent to B, right? Because C is. You can go from C to B in one arrow. That is the definition of adjacency. D. Is C adjacent to D? No. There's no way for you to get from C to D in just one arrow. Is C adjacent to E? Again, no. And then F? Again, no. It's only adjacent to B. Is D adjacent to A? No. There's no way to get from D to A in like one iteration or one hop. I'm calling this a hop. I don't know. I just like calling it. There's probably a very technical way, like maybe transition or something. I'm calling it a hop. Is D adjacent to B? No. Same reason. I'm not going to go over it every time. Is D adjacent to C? Yes. Is D adjacent to E? No. Is D adjacent to F? No. Let's fill out E. So it's going to be a no. This is going to be a no. This is going to be a no. This is going to be a yes. This is going to be a no. Lastly, yes. Lastly, F isn't adjacent to anything. There's no way for there's no direct arrow from F to any other node. Let's fill it all in with zeros. So this is our adjacency matrix. Okay, the other concept is an adjacency list. I'm going to take the same graph and represent it as an adjacency list. You're pretty close, buddy. Just you can live there. Okay, an adjacency list is going to be an array of linked lists. So we're gonna have an index for each one of the elements. So 0, 1, 2, 3, 4, 5. So I'll say A, 0 corresponds to A, 1 corresponds with B, C corresponds with 2, or 2 corresponds with, okay, wait, here. 0 corresponds with any a node adjacent to A, 1 corresponds to any node adjacent to B, or vertices, C to 2, D to 3, E to 4, excuse me, E to 4, and then lastly F to 5. Okay, and this will make more sense. All I'm saying is all the vertices that are adjacent to A is going to be in this linked list. Let's do that. So we're going to have a linked list here. So what elements adjacent to A? Well, we have B. Let's link that up to F. I'll go in order alphabetically. I don't think it matters though. It's just putting in your things you're adjacent to. Oh, we need more room. Okay. And then F. Right. So what do I do here? I have this linked list, and if you're confused on linked lists, watch the linked list video. Right. All the vertices that are adjacent to A are shown here in this linked list. So we have B, E, and F. And I'm fairly certain that the order you place these elements don't really matter. Okay. Next we're gonna have B. So B is adjacent to what? It's adjacent to A. And then it's adjacent to E. That's it. There's nothing else that B is adjacent to. And we can also just fact check this with our table. We only have 2, yeah, for B, or I guess our matrix, not really a table. C only has one adjacency, which is B. D only has one adjacency, which is C. E only has one adjacency, which is D. And then F has zero adjacency, so we're not gonna have anything. That's the linked list for a second, or what we call the adjacency list. That's what we call the adjacency matrix. They both represent the same thing, just in different ways. Now, there's one more graph that I've yet to discuss because I thought it'd be imperative that we studied matrices or understood matrices and lists a little bit better. This is the weighted graph. Weighted graph. Okay, so what is a weighted graph? The weighted graph can be a directed or undirected graph, doesn't matter. I'm gonna make mine undirected, but it could be directed. And you can have adjacency for undirected, or yeah, an adjacency. I think we talked about the adjacency for an undirected graph. There's just two ways, right? So if I was looking at the adjacency from A to B in an undirected graph, at this value, maybe my adjacency matrix, this would be a 1, and then B to A would also be a 1. I mean, I guess in this case it is, but it's just showing that your adjacent, A is adjacent to B and B is adjacent to A. Okay, let's go over the weighted graph. So, I'll give myself some vertex names, I guess. Now, the weighted graph has these numbers. These are weights. These are essentially the cost to travel from one path to another. Like maybe you are going on an outing, right? Across town, and you're deciding on whether you want to go to this B shop or this D shop. And maybe the cost to go to the B shop is it costs you $34 to shop there. Or maybe the cost for the D shop is that it only costs you 6 miles to get there. So, you can go here, or you can go here. That's what I mean by cost. Negative. Well, can we even have that? Yes, you can have a negative cost. Because maybe at C, maybe instead of miles, it's price. I'll do a price example, right? Maybe you're choosing between you're at C and you want to say, so I'm here. Do I want to go to the B shop or the D shop? Well, what if the B shop says, I'm going to charge you $17 to eat here? And maybe the D shop is, I'm going to give you $5, so negative 5. I'm going to give you $5 to eat here, right? And then, if it's just me personally, I would not go to the shop that's offering me money to eat there because that doesn't bode well for my confidence of their, because, yes, that's the whole point of weighted graph. We have these weights now. Going across a path isn't just cheap and easy, there's a cost associated to it. So what does that mean for the adjacency? Why I say we need to learn matrices and lists before we cover this? Well, we have this thing called the cost adjacency matrix. So the cost adjacent, sorry, I'm pretty sure it's just the cost adjacency matrix, right? Yep, okay, cool. I'll just abbreviate it to cost ADZ matrix. So now, instead of storing the values of 0 and 1, so if it's non-adjacent, it's still 0, so this will represent your non-adjacent. Everything is the same in principle, just one fine detail. When you are adjacent, and when we normally have the 1, it becomes 1 times your weight, your cost. Or you could just view that as just being cost. Right, so you can just view that as being cost. So let's go up to this example, let's add some weights. Okay, so if I'm going to add a weight, I have to add it to every single one of these. This will be 3, this will be 3, this will be 2, this will be 1, this will be negative 1, this will be 0, this will be 10, this will be 1000. So I'm only going to do the first row. I'll just update A. A to A is still, there's no adjacency to the same nodes. That's going to be 0. A to B, which what was 1, is now going to be 3 because we have to factor in the weight. Right? When it's 1, we replace it. When it's adjacent, we don't put 1, we put the weight. We're adjacent to E, but if that 1, no, we have to put in the weight, which is 10. We're adjacent to F, which is 1000. So that's how you do it. Adjacency, let's say I had some adjacencies here. It was like what, 10, 1000. Let's do A again. So now in our array list, you would have one more spot for the weight. So A to B costs 3, A to E costs 10, and this is 1000. And then we call like weights. This is no longer the adjacency list, it's called the cost adjacency list. Okay, the cost adjacency list. There's the compact list. I don't think you need to know for UIL though, so I'm not gonna worry about it. You can study if you want on your own time. It's not that bad. Okay, now where these concepts of adjacency lists and adjacency matrices come in handy is when we're talking about sorting, or not searching. There's two types of searches that we can perform. What's called the breadth. I might be spelling this wrong. Oh yeah, I think it's like spelled like this, like bread. So it's the breadth first sorting, or for breadth first searching. This is not a sorting algorithm. No, no, no. This is searching. I don't know why I keep saying that. I'm wrong. So breadth first search, or commonly known as BFS, is what I'll be calling it. So what is BFS anyways? So breadth first search is essentially, it's a breadth first search, depth first search. There the two ways we, or two common ways in which to be tested on tracing true and traversing true a map, right? Or sorry, a graph. So in the breadth first search, we're gonna have two major components. You're gonna have this breadth first search. What is this? In our actual code, this would be like a print line or something, like a print ln. Just printing the console saying we're at this, we started on this vertex, now we went to this vertex, now we went to that vertex. The true fundamental functionality comes from the queue. So breadth first search is also supported by a queue. And have breadth first search and the queue. Now I will have us look at one graph that looks maybe like this. This is our graph. Okay. I'll say A, B, C, D, E, F, G. So I have a couple of notes here. So what we're gonna do is we're gonna go in natural order, so lowest to highest. We're gonna start on 1, or A. A will be added to the queue, or A will be printed out as a starting point and be added to the queue. So in breadth first search, when we reach this node, what do? We visit both of its adjacent children, which is the breadth first component. We visit all of its adjacent children, not children, but adjacent vertices. It was kind of breadth first. We're just going through, like, we're kind of like going through the lot of it, kind of like this. We're really like exploring, kind of. So when we have A printed out, we can say that A is now visited, so I'll denote that with a V. When A is visited, now we can extend this from the queue. So we'll delete A from the queue, and we shall also print out, we'll add B, and we'll add F. Okay, where am I getting B and F from? Well, what's adjacent to A? B and F. So what are we doing? We're removing A from the queue. So we've gone through, we've marked A as visited, we remove it from the queue, and then in its place we on-queue or unqueue B and F because they're the adjacent adjacent vertices to A. Okay, and then you can also say that we visited B and we visited F. Now, what's next on the queue? B. Let's pull that. So when we remove it, now we add all of B's adjacent elements to the list. B is adjacent to A, C, and D, but we only add unvisited adjacent elements. So we visited A, but we denoted A with a V. So we can only visit C and D. So I will draw C, D. They'll also be on queued C and D. And C and D are also visited, so I'll denote that with a V, right? When you're printed out, we call that visited. That is another term, explored. Explored is when you get removed from the queue. Okay, so now F will be fully explored. We're going to remove it from the queue. We're going to add any of F's, like any of F's adjacent vertices that we haven't gone to yet. And there is one, there's E. F is adjacent to E. E is not on here. Let's add E. Also, we shall mark E as visited, right? F was also adjacent to A, but we're not re-adding A. We already visited A. We are not going to add it again. There's no point. So mark that with a V. Then we can check C now. So we finished F. We added all that. Let's go to the next one, which is C. We already have everything C is adjacent to has been visited. That's fine. Move on to D. Let's pull that. Everything D is adjacent to we visited. That's fine. Let's go to E. Well, not everything E has visited we've traveled, right? We haven't gone to G yet. So let's add G. Let's add G. And I switch up the order sometimes. That's just me doing that. Don't really think too much into that. Right, so now we can say G is visited. And then okay, we've done all that. Now let's go back to our queue. What's the next element to remove? Or pull is G. Okay, let's pull G. Is there any elements that we haven't visited yet? No. G is adjacent to E. We visited E. So now is what happened to our queue? Our queue is empty. It's empty. Let's go over that one more time. I'm going to do this exact same example one more time. I feel like maybe seeing it a second time might help clear because I don't think I was that clear in my directions the first time. Let's start over here. So step one, what are we going to do? We are going to print out A. Print out A. Next, we're going to on queue A or offer A. And we're also going to mark A as visited. Then, in probably a for loop, we're going to use either an adjacency list or an adjacency matrix. So we're going to use either one of the two structures that we just talked about to find and to get the elements that A is adjacent to. So after doing that, we'll basically, once we find an element like B, we'll on queue B. So it's on queue B. And then conversely, we'll also print B and mark it as visited. Okay, we find F, right? We on queue F or offer F and we mark F as visited. That's it. Does they have any more adjacent elements? No. So what are we gonna do? We're gonna DQ A. Or well, I appreciate DQ A before this, but I think this is fine. I think it's fine to go about it this way. So I'm gonna go about it this way. This way I think I'm explaining it more clear going this way. Okay, so we've DQ'd A. What's at the top of our list now? It's B, right? Okay. I know I said I know I do DQ A last. Really, once you visited A and such, before we get to the adjacent nodes, we DQ A. So A is removed off the list, and then we're gonna add in onto B and F. Okay. All this is still good. I just want to specify that so this next part isn't get confusing. Okay, so we've done A. A's done. We had all of its adjacent elements. Well, what's next in the queue? The new head is B. Let's pull B. Okay, so when you dequeue it, the next step after dequeuing is adding all of its or onqueuing all of its adjacent elements, which would be C and D. Add C. Also, we're gonna then at the same time we're gonna print out C, mark and denote it as visited, and we're gonna print D or onqueue D, then print D and denote it as visited. And also you're seeing that I'm going in from B, I'm not doing D then C, I'm doing C then D. We're going in the lexicographical order. Okay, B is done. So now let's move on to F. Let's DQ F. F, okay, should it be this? Should I on Q A add A? No, 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 we should not do that. We even mark things as visited because in reality we're this visited array that actually holds all these values referencing them as an index, right? So it'll hold, it has an index for A, index for B, C, all that, right? It's gonna look through there and see, hey, is the in the index we have for A, is that one? If it's a one, that's what visited is. So when we say we're denoting something as one or as visited, that means we're going to its location in the visited array, its index, and setting that to one. And we can't actually when we reach F, we're not gonna go to A, right? Because A is already visited. We're gonna go to E, which is our unvisited vertex. So we're gonna onqueue E, we're gonna make E visited. Okay, that's it for F. Let's dequeue C. Well, actually we visited everything in C. There's nothing else for us to do. Let us dequeue D. We visited everything in D. There's nothing else for us to do. Let's dequeue E. We haven't visited G yet, right? We visited F, visited D, but we haven't visited G. So let's add G, onqueue G, and then at the same time print out G and mark it as visited. So now that's it for E. Let's move on to G. Let's DQ G. Okay, we have E. That's the only thing it's adjacent to. That's it for G. And then this is our breadth first search. Now I don't know if UILCS will test you on this. They might. They call the breadth first search spanning tree. I'll cover spanning trees in detail in the next video, but I want to cover this here. It's just simply a binary tree made up of the elements B, then maybe I have F. I don't think it really matters if you choose this side or that side. Because it's a binary tree, you have to have two children and they don't specify completeness or anything like that or fullness. So I'm gonna make mine look like this. I want it to. All we're doing is just creating a tree, going this, adding it as it shows up in the breadth first search. We call this a breadth first search spanning tree. Now, if you're confused on what spanning is, that's understandable, but just wait for part two. Part two will make sense. Let's go over depth first search. Depth first search. This is also known as DP, DFS. I don't know why I keep getting, or why I keep saying DF, or DPF. We're gonna use the exact same one, because I'm lazy. Why am I trying to take a snipping tool screenshot? I had to select the tool. Let's drag it down a bit. So it's over here. Okay, depth first search is a little bit different. Instead of using a queue, so DFS is going to represent our printout. Ooh, this looks like far away. I guess you can write stuff here. So we'll write DFS here. We're not going to use a Q. We're going to use the stack. So I'll draw my stack like this, and I'll just erase this for now. Good, my ratios learned to stay on the biggest size. Okay, length's a little weird to say for that, so okay, how does DFS work? Well, in breadth first search, we're going to start with A, right? We're going to start with A. In breadth first search, then we essentially had A on a Q. We popped A, then or we pulled A, and we unqueued its adjacent elements. In depth first search, we're just going to go to one of the adjacent elements, B, and then from B, we're going to go to its adjacent element, C, and so on and so forth, right? However, let's say after we find that A has adjacent element B. Once we know A has an adjacent element, probably to our adjacency list or matrix, and we've printed it out, then we're going to add A to the stack. And we'll do the same thing, right? When we get to B, we see it has an adjacent C. We'd add C, and we'd push B to the stack. So let's run through this example. So we're going to have DFS of A printed out, then check does A have adjacent element? Yes, it does. We're going to go to B because we're following lexicographical order. We're going to add A to the top of our stack. It's be right here because we're going to add more elements. But this is like our top. Here I'll draw like this. A, the top of our stack. Next we're going to go to B. So we're just throwing that in a stack. That's fine, whatever. All right, we're going to B now. We're going to see does B have any children? Or not children, but adjacent vertices. Or vertices, yes, we have C. Let's go to C. And now let's make B the top of the stack. We'll give some room. Actually, let me do something like this. Okay. So now B is the top of our stack. C, does C have any children? We're on C now, or adjacent vertices. Yes, C is adjacent to D. But let's C to our stack. So now C represents the top of our stack. Let us see, does D have any adjacent elements? Yes, that's B, that's C. But also make sure, I forgot to denote, these are all visited. The visited array is still a very real important thing in this. Right, these are all visited, so we're not going to go to B, we're not going to go to C. But hey, wait, D exists, right? We're going to go to E. And then so we're going to also then do what? We're going to push D to the stack, right? Once we know that D has an adjacent element, or adjacent vertice, we're going to push to the stack. Next, E. And E will be visited. Well, we have F and G as our adjacent unvisited vertices. So let's go to F because we're going lexicographically here. Also, a really big line. F. Let's denote that it's visited, and let's add E to the stack. Right? E, we found that E has adjacent vertices, so we're just gonna print out that we're gonna move on to adjacent vertices and print out and add E to the stack. Okay, moving on. F. F has no. Wait. What do we do now? Right? F has no more unvisited adjacent vertices. You visited everything F has. So we're simply gonna push E from the stack, or pop E from the stack. So now we're back to E. We've gone from F, like we're here now, right? Maybe on a search you could say we went from here, hopped here, hopped here, hopped here, hopped here, hopped here. Now we are hopping back here, right? If it helps you, you can also kind of do this recursively. This is all recursion, and we're going back one. So maybe we've reached the base case here, we're going up one, right? Okay, we're at E now, right? We're gonna say, does E have any other unvisited adjacent elements? Yes, it does. That's G right there. So let us add G. And because we found that E has an adjacent vertex, we're gonna add E to the stack. That rule still applies. Now we're on G. Does G have any adjacent vertices? Nope. So what we're going to do when that happens, we're going to pop E out of the stack, check if E has any adjacent vertices. Well, actually, oh, this is visited too. Any adjacent unvisited vertices is what we're checking for. No, not anymore. Everything's visited. So, hey, okay, let's try D. Let's pop out D now. Let's pop out the next element. Does D have any adjacent elements? No. Okay, let's pop out C. Same thing with C. B. Same thing with B. A, same thing with A, and then your stack is empty. I kind of like to look at it as, oh, we have E, and then we go to F, and F doesn't have a adjacent vertex, so it goes to crank its parents to try and get its parents to like solve its problem and find an adjacent vertex, and then E manages to find one, but then G same thing. That's kind of how I like to look at it. It's just a stack. Also, when we code it, it's coded recursively, so that'll be cool. Okay, so we have covered the depth first search. Oh, now let's also, you can make a depth first search spanning tree. So we have a node A, a node B, just like this. Maybe here a node C, A, B, C, right? Then maybe I'll have D here. Let's go E, and then F. Oh, so we actually got it alphabetical. Don't think it's like a sorting mechanism. It's not. I just got lucky and it's alphabetical. I guess it makes sense why it'd be alphabetical. This one wasn't because we went through every node, but this one, yeah, this one makes sense. It's not always going to be alphabetical though. It just depends on the graph. This one was. It's not a pattern. Don't think it is. Just know the algorithm. Anyway, so this is a depth first search spanning tree. So is this hard to make? Nope. What does it require? You knowing how to do a depth first search, you knowing how to draw circles, alphabetical letters, and lines. That's it. Just the name is confusing. That's the only confusing part about it. This is a depth first search spanning tree. This is a breadth first search spanning tree. Okay, so let's code breadth first search and let's code depth first search. So I'm just gonna code them here maybe. Let's delete the sid heap stuff. Heaps, cool. Should watch a video on heaps. They're pretty cool. And you learn priority queues too, which are really important to know. Oh my goodness, does UIL love testing priority queue time complexity. You're never gonna figure this out. You're never gonna figure out its O log n for everything. Except for the obvious ones. I guess not. But watch the video, watch the video. I'm just yapping, bro. Public. So first okay, public void collect breadth first. Search. And whoa. Can we even start here? No, we need an adjacency list or an adjacency matrix. I'm going to create a linked list of integer. Look at this. Adjacency list is going to be equal to new linked list of integers. Do we need like a capacity? Okay, 5 elements, I guess. I want integers. Fine, I'll leave it like this. I don't care. So let's use this graph actually. Or shouldn't we already have a graph made? No, let's use this one. It'll be good practice. So what would the adjacency list for this graph look like? Let's go over it together. A would have connections to B, connections to C, or connections to F. B would have connections to A, connections to C, connections to D. We're going to store them lexicographically here. So it's easier for us. That is brown. C has connections to B, has connections to D, has connections to F. Let's move on to D, has connections to C, or sorry, B, then we do C, and then we can do E. Okay. E has connections to D, F, G. D, F, G, and lastly, F has connections to what? Or not lastly, we still have the other one. A, C, E. Okay, lastly, G has connections to what? Just E. By connections are meant adjacency. So let's represent this. So I'll say index 0 adds list 0 is equal to new linked list dot f. And I'll add in the elements, that being, oh, we did the letters, right? I can make this a string, that's fine. B, comma, F, copy this over. 1, 2, 3, 4. Let's do this one for now. So BF, then ACD, ACD. I think the other one I saw was like BDF, BCE, DFG. So DFG. Next we have ACE, and then we have E. So this will be an A, a C, an E. And then lastly, this will be 6. I will say that this is going to be E. And I messed up the size of the linked list. I just put down 5. If you're using this graph, we need 1, 2, 3, 4, 5, 6 spaces because the amount of spaces you have should be equal to. Or it should be maybe plus 1 then the amount of elements you have because we're going A, B, C, D, E, F, G. Okay, so wait, do we have? Yeah, we have 7. Wait, I'm just bad at counting. No, it is right. 1, 2, 3, 4, 5, 6, 7. You have 7 elements. The length of your adjacency list is 7. That's how that works. So, okay, we made our adjacency list. Let's pass it in as a parameter. Let's think. Do we need any other parameters? You could say starting index. That'd be acceptable. I'm starting mine always at A. So, how does Bedford search function? Let us review. We need to print out A, we need to mark it, we need to add it to the queue. So I need a few things. I need a queue, data structure. We use the sid queue, guys. Yo, let's run a sid queue. Type string, call it queue, equal to a new sid queue. And capacity size is 7. Right, because if you saw the video on queues, we made an array. We made the array backed queue. We didn't make a linked list queue. We made an array backed queue. And then I need to firstly this out. Let's just print out the element. So this. Let's use a bit of printf syntax. I don't want that to be lost or foreign. You know what I mean? Adjacency. Let's just print out adjacency list. Let's print out A. Wait, I know what it is. It's freaking A at the start. This A, this is B, this is C, this is D, this is E, this is F, this is G. And then also I would like a integer array visited, new integer array of type 7. So I'll just slot every single element. So that's what we need. Excuse me. So how does this work? Let's first start by doing q.offer a. So now a is offered to the queue. Then let's do while. So what's this while loop? It's probably while q dot is empty. Or did I say q dot? Do I not have an empty method in my queue? Let's go and make one. Where is set queue? I think I didn't add is empty because low-key, like, who needs that, bro? But it would just be this public boolean is empty. So it is empty here. Stack calls it empty. So our boolean is empty when size is equal to 0. So our return size is equal to 0. Okay. So while this is false, let's go in here and it's while loop. So firstly, we need a q dot poll a q dot poll. So what happens when poll is be like string poll is equal to this. This will give us a. We need to go and find a's adjacency list, and we need to onQ b and onQ f. So how can we do that? It might be easier if I use a system of numbers instead. I could just say go to adjacency list this, relationship list this, relationship list that. I'm gonna take advantage. I'm gonna create an int size equal to 0. Int index equal to 0. So for it should be string lm in adjacency list of the index. Let us first print out lm. Will this work the way I want it to? Because when we get to f, we need to use this to find. So we need a relationship between this and this. We need a way to say, when I give you f, know that it means 6. When I give you... Oh, we could do that. We could do that easily. Wait, guys. So I will say, simply, let's do a little bit of work. This is going to return a string. I'm going to say character poll is equal to poll.car at 0. This is what we've pulled. This is the character. I can say int is equal to int num is equal to poll. So a is represented as 65. If I want this to be 0, I can subtract 65 from poll. So say minus 65, give me this number. And then I can simply pass in that number here. There's no need for this. This will give us where we're looking at the adjacency thing. Then we'll simply just print out that lm. I'll use this because I want to see it practicing with it. Let us q.offer then this lm. And that should be that. We're gonna go through all of it, then we're gonna offer it. We're gonna print out, we're gonna offer it. Then Q is not empty. Let's pull the next one. Let's do the same process. Let's repeat this. Ooh, and then once so I'll set, we need to set right now, visited, right? We have to do visited is 1. So let's say for this, if visited at num is equal to 0, then you can print out stuff out. And then let us set visited at this num equal to 1. Okay, so let us call breadth first search on our adjacency list. Boop. Let's call this A. Wait, does Q is empty work? I mean, I made it, so who knows, bro? Yo! Why is that not working? Let's go to the sid queue. We add an element. We increment size, or what? Let me go to offer. Oh, I'm stupid. This should be this. This. Or no, this should be this. No, I'm right. I'm right. This should be this. Just fine. That's fine. That actually should be false. That means it's working. We pull it. And can I print out num 0? Can I print out arrays dot toString adjacency list at num? Oh yeah, we don't need that. It's an adjacency list. Let's just print it out. It's a linked list. Let's print it out normally. B and F. Ah, this should be, I'll create a new integer. I'll call it visited num should be equal to, and I'll just take all of this and make it one line. So say lm.car at 0 minus 65. Let us write this. I'm going to remove the unnecessary prints I have. Let's remove this new line too. And this is a visited num here as well. A, B, F, C, D, E, G. Right? We are matching. So we have completed the breadth first search algorithm. This is definitely a different approach, but that's the thing with coding is different approaches work. I feel like maybe another approach if you use the matrixy might have been easier because you have a relationship, right? You know, density matrix 0 is A, density matrix of 1 is B. I guess how would I even work with that too? Oh, cause you can check with your number, like it'll point you to the next number and you just go there, which is why I see. Okay, you could do it like that. If you're making your matrix of numbers, you could take whatever number you had, subtract it by 1, and I guess that might not work yet. I guess it depends on your approach. Like when I was watching a guy code it, that's how he did it because he used like this. I'm using my SID queue and doing it with strings. So, but I like this approach because it reminding you on chars, reminding you on queues, reminding you on printf. We're going over some you know how you can use characters to subtract as like this, right? Because characters are really integers. Okay, that is breadth first search. Maybe depth first search, I'll code it a little bit more standardized. So I need the adjacency list. And well, let's think about this, right? So, and I'm gonna need the previous index, index, maybe. How should this work? Looking at depth first search, we went to A, and if A had a child, we called depth first search on B, and if B had a child, we called depth first search on C, right? So let us start off by doing something I know we have to do. I'll do suf %s in A. We're gonna print out A, okay? Then we need to call depth first search on B. Let's run depth first search, adjacency list, index 1 for B. But this is going to get stuck in a loop because it's calling B an index. We need to find a way to calculate the next index. So what is the next index? That's a good point, Sid. Well, the next index is going to be something like this, right? I'll just copy this code over. It's going to be the next adjacent section. That's right, we had a bunch of stuff going on. Let's pass in num. And then we also need to pass in visited. Okay, so then in here, if this is a new visited element, what we can do is we can, well, this won't really be that for search. We need to assign a visited of num equal to 1 here. And then inside of here, we need to call adjacency list with visited num. Oh, and then we need to pass in visited num. I think that might be the algorithm done, maybe? Car at 0. LM though, so that should work. Let us test. Adjacency list. That's an array, so I'll do new and okay, where was I? Yeah, let's test this. I'll make it a new int array of 0, 0, 0, 0, 0. And then what should the size be? It should be 7, right? It's 1, 2, 3, 4, 5. We have 7 elements. So 7. So we have this size length, right? We're not creating one in here, we're using one passed in. We'll set it for a number of 0. So this will give us A. So something right here, this shouldn't be A. This should be, what should this be? Well, what is it here? It is the elem. It is the elem at visited num, I guess. Should we pass in the element 2? What if instead of passing in the number, we passed in a string called the elem? We printed out elem here because we can find a number by doing all of this stuff, right? How did we find a number before? For num. We did all of this math, right? So we can just do elem dot car at 0 minus 65. That will give us a proper value. I'll take u though, and I'll just call you num for simplicity. let's paste you here. And we're struggling because I called this LM. Let's call this LM1. And we're struggling because I'm passing in a string LM. So, and I'm getting an error here because this should be a string A. A, B, C, D, E, F, G. Boom. Alright, depth first search done. Depth first search finished. Breadth first search finished. So we can compare the two algorithms side by side. Just list. This one uses recursion. It's essentially doing the stack behavior, right? We go until we keep on going in the thing until we can't anymore, until we've visited everything, then we'll just go back to our parent, right? We pop off the stack, as you saw in the example. It's recursion, that's all it is, it's recursion. So yeah, you can see A, B, F, C, D, E, G, which is what we got. We said it should be A, B, F, C, D, E, G, which it is, A, B, F, C, D, E, G, and we should say this bottom should be A, B, C, D, E, F, G, which it is. So this was breadth first search, depth first search, and graphs. Hopefully you enjoyed it.